to the material, the other thing which kind of governs the behavior of a member is the boundary conditions, right? So for example, if you so any structure, they will actually have different supports, be it a pinned support, be it a roller support, be it a fixed end support, or it could be springs as well. So we'll just kind of look at some of those and what are the different aspects of that, and then how do we actually what are the different real life examples of these kind of boundary conditions, right? So the first one that we could, and then also one more thing I would like to bring up here is like, so any support would actually induce a reaction load only in that direction, wherein it is, kind of locking or restraining a particular degree of freedom. And that's how that distress is actually developed in the support. So for example, if we look at this first one here, that's we're actually talking about a pinned end support here, right? So what this does is like it actually locks all of the different degrees of freedom of translation in all the three directions. So that's what I'm showing here, like Rx, Ry, and Rz. So that's the reactions that this pin support would actually produce in X, Y, or the three-dimensional direction, because it kind of locks the translational degree of freedom of a member in when a member is having this kind of support. And a real life example of this support would be, say for example, if you have a say a steel beam to a steel column connection, which is like a typical or normal shear type connection. In that case, the kind of support that qualifies as is a pinned support, wherein that shear type connection is not really, it's kind of prohibiting like movement of that beam at that end in all the three directions, but it's still allowing rotation of that joint about that direction. So it's not really prohibiting any rotation of the member about the joint, but it's just translational degrees of freedom which are kind of restrained. So that's one example of this one here. The other is, say, a roller support, right? So in roller support, what happens is we actually just lock 1 degree of freedom of translation, and that is basically normal to the surface on which this support is bearing. So if you see in this diagram here, only Ry is produced. That's because Ry is basically the direction, the reaction that's produced in the vertical direction. So it kind of locks the degree of freedom in that direction only, but it can still, glide easily or slide easily in the plane of paper, say east-west, or maybe into the plane of paper or out of the plane of paper. And a good real life example of this kind of support would be, say, if you have an expansion joint and then you have a beam crossing an expansion joint in a structure. In that case, that beam has to be, kind of seated on a roller support, which is like a bearing pot or something. And the reason for that is you don't really want to, given it's an expansion joint, so the intent of an expansion joint is to be able to, not transfer any lateral loads induced in the two structures from one structure to the other. So in that case, you actually require this kind of support there, so that that beam or a member which is actually spanning across an expansion joint does not end up transferring any, say, lateral force from one structure to the other. So that's one example of a roller connection. I mean, there are a bunch of different other examples as well, like in the bridge industry as well. So that's a roller support. The other one is a fixed end condition, wherein all the 6 degrees of freedom, like all the 3 rotational degrees of freedom, and then all the 3 translational degrees of freedom, so they're all actually locked, and therefore that joint actually produces reactions in those corresponding directions. And this is a very common support again, which is used, say, in a moment frame system, for example, wherein if you have a beam which is connected rigidly to a column, so in that case all the 6 degrees of freedom are actually kind of not locked per se, but then you still develop all these 6 forces over there because you have that restraint internally. But then from a support condition standpoint, say if you have a beam which is moment connected to a column, for example, say if you consider RCC beam, wherein you have designed, and that's a cantilever beam, and then you have designed that beam to take care of that moment, right, which is developed as a fixed end. So that's a good example of this kind of boundary condition. So that's that. And then lastly, I would also like to kind of touch upon the internal hinges, which is not really a boundary condition per se, but then it's more like additional equation that we get when we are trying to solve all the equilibrium equations. Because in an internal hinge, what happens is that internal hinge can just transfer only shear reaction from one member across to the other, but then it can't really transfer any moment at all. And a good real life example of this would be, so in the US, what happens is, like, typically, say you have a beam, for example, which is, say, 70 to 75 feet in length. But then in that case, the thing is, the maximum shipping length of that beam or members in US may be like 40 to 60 feet, right? But then this beam, for example, let's say 75 feet in length. In that case, you can't really ship this entire piece. So in that case, what you would do is you would end up splicing that beam here. So if you have a splice connection here, that splice could be a shear type splice, or it could be a moment splice, wherein if it's a shear splice, that's more like an internal hinge, where it would just transfer shear across from one member to the other. But when it's a moment type hinge, in that case, you also make sure like there is continuity in moment as well. So like these are a few possibilities that we have in terms of achieving the different degrees of freedom and the boundary conditions in a given structure. So let's just now kind of try and cover some of the basic types of beams that we already might be aware of, but just to kind of touch upon them. So like the first one would be, say, a cantilever beam, which I talked about before, wherein you have a beam which is having a free end at one end, and then you have a fixed end at the other end, right? So that's what I've denoted here. Like we have a fixed end on the side, for example, and then a free end over here. So that means when we say free, that means that joint is actually has no degree of freedom which is logged. But then when it's a fixed condition, that means all the 6 degrees of freedom are actually logged. So that means whatever load is applied on this beam, on this cantilever beam, so this moment reactions here will actually try and equilibrate those forces. So this joint here could develop the translational reactions as well as rotational reactions. So that's what this beam is, and this is really a common kind of a beam, for example, which is seen, say, even in canopies. So canopies would be one good example where you would see a bunch of cantilevers, and the other would be, say, in residential projects, you would see balconies which are kind of cantilever of our floors. So in that case, though, beams which actually pick up those balcony floors and all, they're actually cantilevers. So that's one good example of a real life cantilever structure.